You are never leaving this solar system. Not you, not your kids, not your grandkids, not anyone alive for the next 10,000 years. And there is a real chance no human ever in the entire future of our species sets foot around another star. Not because we lack the will, not because we lack the imagination, but because the universe itself is built in a way that makes it almost physically impossible. Stick with me for the next 50 minutes, because by the end of this video, you are going to look at the night sky completely differently. And I promise you, there is a twist near the end that changes how you think about all of this. Let's start with something that sounds insane until you actually do the math. The nearest star to our sun, Proxima Centauri, is about 4.24 light years away. That sounds like a number you could wrap your head around. It isn't. A light year is not a unit of time, it's a unit of distance, and it happens to be roughly 9.5 trillion kilometers. So 4.24 light years is about 40 trillion kilometers. If you got in a car right now and drove at highway speed, non-stop, no sleeping, no gas stops, forever, it would take you over 50 million years to get there. Voyager 1, the fastest object humanity has ever sent away from Earth, launched in 1977, has been flying for nearly 50 years, and it still hasn't left our solar system's outer gravitational boundary. At its current speed, it would need roughly 75,000 years just to reach Proxima Centauri, and it isn't even pointed in that direction. That is the scale we are dealing with. Not a hard trip, not an expensive trip, a trip that outlasts civilizations. Now, most people hear that and think, okay, but technology improves, right? We went from horses to airplanes in a single human lifetime. Surely we'll figure out something faster. And I understand that instinct completely, because it's the instinct that has been right almost every single time in human history. But space is different, and it's different in a way that most people never actually sit down and calculate. So let's calculate it together, because once you see the actual numbers, you'll understand why so many physicists, not science fiction writers, not doomers, actual working physicists, have quietly concluded that interstellar travel for biological humans might be a permanently closed door. The first wall we hit is called the rocket equation, and it is, without exaggeration, one of the cruelest pieces of math in all of physics. Here's the problem in plain language. To accelerate a spacecraft, you need fuel. But that fuel has mass, and mass needs more fuel to move it. So you add more fuel to carry the fuel. But now the extra fuel also has mass, so you need even more fuel to carry that. This isn't a small effect, it's exponential. It means that if you want to reach very high speeds, the amount of propellant you need doesn't grow in a straight line, it grows exponentially, to the point of absurdity. To get a modest spacecraft up to just 10% of the speed of light using chemical rockets, the kind we use today, you would need a mass of fuel greater than the mass of every planet in the solar system combined. Not an exaggeration for dramatic effect. An actual consequence of the math. Chemical rockets are simply, mathematically, never going to get us there. Full stop. So, okay, chemical rockets are out. What about nuclear propulsion? This is where things get a little more interesting and a little more real. In the 1950s and 60s, a group of very serious American scientists worked on something called Project Orion, a spacecraft design that would be propelled by detonating small nuclear bombs behind it and literally riding the shockwaves forward. It sounds like something out of a comic book, but the engineering was legitimate, and on paper it could reach a meaningful fraction of the speed of light. Somewhere around 3 to 5%. The project was shelved, partly due to nuclear test ban treaties, and partly because, well, building a spacecraft that works by exploding nuclear weapons behind a crew of humans raises some understandable safety concerns. Even in the most optimistic version of this technology, 3 to 5% of light speed would still mean a journey to Proxima Centauri taking somewhere between 80 and 140 years. That is longer than a human lifetime. That is not a mission. That's a one-way exile. Then there's fusion propulsion, which is what most serious interstellar mission proposals, like the real-world Breakthrough Starshot and Project Daedalus concepts, actually rely on in their design documents. Fusion is incredibly powerful. It's literally the process that powers every star in the universe, including our own sun. The problem is, we have never, not once, in the entire history of human technology, built a fusion reactor that produces more energy than it consumes for a sustained period of time. We're getting closer. Ignition experiments have made real progress in the last few years, but turning a laboratory fusion reaction into a compact, self-sustaining engine capable of propelling a multi-ton spacecraft to 20% of light speed is a leap we cannot currently see the other side of. It might happen in 100 years. It might not happen in 1,000. Nobody actually knows, and anyone who tells you they know is guessing. And then there's antimatter, which shows up in almost every serious paper about interstellar propulsion, because on paper, it's the perfect fuel. When matter and antimatter collide, 100% of their mass converts directly into energy, which is the most efficient reaction physically possible in this universe. The catch, and it is an enormous catch, is that antimatter is the most expensive substance ever produced by human beings. We can make antimatter in particle accelerators, but only in tiny quantities, individual particles at a time, at a cost that would make a single gram of antimatter cost more than the entire combined economic output of the planet Earth for several years. We are not talking about an engineering problem we can throw money at. We are talking about a fundamental production bottleneck that, even with wildly optimistic future technology, would take centuries just to manufacture enough antimatter for a single one-way mission. Now, at this point, somebody always brings up wormholes, or the Alcubierre warp drive, the idea that instead of moving through space at high speed, you bend space itself around a ship so that the distance between 2 points effectively shrinks. This isn't nonsense. It actually comes from a real solution to Einstein's field equations, published by physicist Miguel Alcubierre in the 90s. On paper, it technically doesn't violate relativity, because the ship itself never exceeds the local speed of light. Space is just doing the moving. It sounds like the perfect loophole, except the math comes with a catch so severe that most physicists consider it functionally as impossible as anything we've discussed tonight, because every known version of this solution requires something called negative energy density, matter with genuinely negative mass, which, as far as every experiment ever run in the history of physics can tell us, does not exist anywhere in this universe in any usable quantity. A tiny quantum scale hint of something similar shows up in an obscure effect called the Casimir effect. But the amount of negative energy that effect produces is so vanishingly small and so far removed from what would be needed to warp space around an actual spacecraft that comparing the two is a little like comparing a puddle to the entire Pacific Ocean. Wormholes have a nearly identical problem. They're mathematically permitted by general relativity, but every calculation for keeping one open long enough and wide enough for a spacecraft to pass through also requires exotic matter with negative energy density holding the throat of the wormhole open against its own tendency to collapse instantly. We're not talking about an engineering problem here either. We're talking about needing a form of matter that has never once been detected to exist in any meaningful quantity anywhere in the observable universe. It's not that we haven't built it yet, it's that we have no evidence it can be built at all. There's one more idea worth addressing honestly, because it's the one actual working scientists at places like Breakthrough Starshot are pursuing right now,
10,
today, with real funding and real prototypes.
6,
And it's important to distinguish it from everything we just ruled out.
2,
Instead of
1,
trying to accelerate a heavy spacecraft carrying humans,
liftoff.
the idea is
Space
to
Shuttle
build an
Discovery,
extremely
taking the
lightweight
space station
probe,
to full power
something
for
roughly
full
the size and
science.
mass of a smartphone chip, attached to an ultra-thin reflective sail only a few meters across. Then, instead of carrying its fuel with it, you fire an enormous ground-based laser array at that sail from Earth, pushing it to relativistic speeds using light pressure alone, potentially reaching 20% of light speed. within just a few minutes of acceleration.
Discovery flying
This is genuinely one of the
365
most
miles per
promising
hour,
interstellar concepts on the table.
1.5 miles in altitude,
And unlike
7 miles
wormholes
downrange
or
from the Kennedy
antimatter
Space
engines,
Center.
it doesn't require any
Discovery's
physics we haven't
engines are
already
throttling
confirmed
down as the
exists.
orbiter passes through the
But
area of
notice what it
maximum
actually
pressure on the
solves
vehicle.
and what it doesn't. It could, plausibly within our lifetimes or our children's lifetimes, send a tiny robotic probe to Alpha Centauri and get images and data back within about 25 to 30 years round trip for the signal. That would be one of the greatest scientific achievements in human history, and I genuinely believe we'll see it happen. But it does absolutely nothing to solve the problem of sending a living, breathing human being anywhere. You cannot shrink a person down to the mass of a postage stamp. Every gram of additional mass you add to that sail, life support, food, water, radiation shielding, a way to decelerate at the destination instead of just flying past it at 20% light speed, multiplies the required laser power and cost by orders of magnitude. The probe version of interstellar travel is realistic. The crewed version remains exactly as far away as everything else we've discussed tonight. So let's be generous. Let's imagine, just for the sake of argument, that a few hundred years from now, humanity solves fusion and somehow builds a spacecraft that can reach 20% of the speed of light, which is already far beyond anything currently on any engineering drawing board. That ship would reach Proxima Centauri in a little over 21 years. That actually sounds almost doable, right? 21 years is a long mission, but astronauts have spent a year on the International Space Station, and 21 years, while brutal, at least sounds like it's within the realm of a human lifetime. So let's talk about what would actually happen to the human beings inside that ship. Because this is where things get genuinely disturbing. Space is not empty. I want you to really sit with that sentence, because most people picture space as this pristine, silent vacuum with nothing in it, and that picture is wrong. Interstellar space contains scattered atoms of hydrogen, helium, dust grains, and occasionally larger debris, all left over from the death of ancient stars and the slow churn of galactic material. At normal speeds, this stuff is harmless. You could fly through it your whole life and never notice. But at 20% of the speed of light, everything changes, because kinetic energy scales with the square of velocity. That means even a single grain of dust, something smaller than a poppy seed, hitting your ship's hull at that speed releases an amount of energy comparable to a small explosive detonation. A pebble the size of a golf ball hitting your ship at that speed releases more energy than the atomic bomb dropped on Hiroshima. Your spacecraft isn't flying through empty space, it's flying through a minefield for 21 straight years, with absolutely no way to see the mines coming. Because at that speed, you have no time to react, even if your sensors could detect a grain of dust light seconds away. Now, let's add radiation into the mix, because this is the part that even a lot of space enthusiasts underestimate. On Earth, we are protected by two enormous invisible shields, our planet's magnetic field and our thick atmosphere, both of which deflect and absorb the vast majority of dangerous cosmic radiation before it ever reaches us. Astronauts on the International Space Studies on astronauts who've spent extended time beyond low Earth orbit already show measurable cognitive effects, memory problems, and elevated cancer risk. Now imagine that exposure, uninterrupted, for 21 years, with no planet to duck behind, no magnetic field to hide inside. Some estimates suggest that without radical new shielding technology, we do not currently possess, even in theory. A crew on a multi-year interstellar voyage would face a near certainty of fatal radiation sickness or cancer before they ever reached their destination. Lead shielding thick enough to meaningfully protect a crew would be so heavy that it would defeat the entire purpose of trying to build a lightweight, fast spacecraft in the first place. It's a trap with no clean exit. Heavier shielding means slower ship. Faster ship means thinner shielding. There is no version of this equation where you get both survival and speed, and I haven't even gotten to what zero gravity or even partial gravity does to the human body over that kind of timescale. We already know from decades of research on the International Space Station that extended time in microgravity causes serious, measurable damage. Astronauts lose bone density at a rate of roughly 1 to 2% per month, comparable to osteoporosis in elderly patients, except it happens to healthy young astronauts in their 30s and 40s. Muscle mass withers without constant, grueling exercise regimens. The heart, which no longer has to work against gravity to pump blood upward, physically changes shape and weakens. Fluid shifts toward the head cause changes in eye pressure that permanently damage vision in a significant percentage of long-duration astronauts, a condition doctors now call spaceflight associated neuroocular syndrome. The immune system becomes measurably less effective. And this is all documented from missions lasting, at most, about a year. Multiply that by 20 across multiple decades, and you are not talking about minor inconvenience. You are talking about a crew that, if they even survive the trip, would arrive at their destination as physically devastated individuals, potentially unable to walk under any gravity at all, let alone explore, build, or farm on a new world. Let me pause here for a second because I think this is a good moment to ask you directly, before we go further into the human cost of all this. Knowing what you know so far, the rocket equation, the dust collisions, the radiation, the fact that even our best real proposal only gets a tiny unmanned probe to the nearest star, would you personally get on that ship if it existed tomorrow, knowing you would never see Earth again, and knowing there's a real chance the trip itself could kill you before you arrived? Type your honest answer in the comments, yes or no, and tell me why. Because I think the answer says a lot about how each of us actually weighs adventure against survival. And I want to see how split this comment section actually ends up being. So even in our most generous scenario, 20% of light speed, a fusion engine we haven't invented yet, a radiation shield we can't currently build, a hull that somehow survives a 2-decade minefield of interstellar dust, you still end up with a crew whose bodies have been so degraded by the journey that arrival might functionally be a second disaster on top of the first. This is why, when actual physicists talk about interstellar travel, the conversation almost always shifts away from sending fully grown adult astronauts and toward much stranger proposals, generation ships, cryogenic freezing, or sending only embryos and artificial wombs to be raised by robots on arrival. I want to take a moment on each of these, because they sound like clever workarounds, and they get thrown around constantly in comment sections under videos like this one, but each of them has its own brutal, often overlooked problem. Generation ships are exactly what they sound like. A spacecraft large enough to be a fully self-contained, permanently closed ecosystem where the people who leave Earth will never arrive anywhere, but their great-great-great-grandchildren, born and raised entirely inside a metal tube, hurtling through the void, eventually will. On paper, this solves the lifespan problem, because no single person needs to survive the whole trip. In practice, it introduces a nightmare of new problems. We have actually tried to build small-scale closed ecosystems here on Earth, most famously in the Biosphere 2 experiment in Arizona in the 1990s, where a crew was sealed inside a sprawling, custom-built glass and steel structure with the explicit goal of creating a fully self-sustaining habitat. It failed. Oxygen levels dropped dangerously low. Unexpected species died off, throwing food chains into chaos. Insects intended to pollinate crops died out entirely. Carbon dioxide levels spiked. And this was on Earth, with a support team standing right outside the walls, ready to intervene, and full access to fresh replacement supplies if things got desperate. A generation ship would have none of that. No backup team, no replacement parts flown in. No way to call for help that would arrive in less than 4 years, even at the speed of light. And by the time an answer came back, it would be too late for whatever crisis triggered the call. Every single failure point, every mechanical breakdown, every crop disease, every unexpected genetic mutation from generations of radiation exposure, every psychological crisis among a permanently isolated population would have to be solved internally by whoever happened to be alive on the ship at that moment, using only what they brought with them centuries earlier. We actually have real world data on what long term isolation does to groups of otherwise healthy, carefully selected, highly trained people, and it should make anyone nervous about a multi generational voyage lasting centuries. Researchers who study Antarctic winter over crews, small teams of scientists and support staff who spend months completely cut off from the outside world in permanent darkness, unable to leave even in a medical emergency, have documented a recurring pattern they sometimes call the third quarter effect, a predictable dip in morale, cognitive performance, and interpersonal cohesion that shows up roughly 2/3 of the way through an isolation period, regardless of how well trained or psychologically screened the crew was beforehand. Submarine crews on extended deployments show similar patterns, along with measurable increases in irritability, sleep disruption, and interpersonal conflict the longer a mission drags on, even among elite, handpicked military personnel selected specifically for their psychological resilience. And these are missions measured in months, with a guaranteed return date, a support network waiting on the other end, and the psychological comfort of knowing rescue is, in the worst case, still theoretically possible. A generation ship offers none of that. No return date, no rescue, no endpoint that the people living through the hardest years of the journey will ever personally see. Historian and sociologists who've studied isolated closed communities across history, from actual multi-year polar expeditions to religious communes that tried to build fully self-sufficient societies cut off from the outside world, consistently find the same failure pattern emerging over long enough timescales, fracturing into factions, authoritarian leadership taking hold under the justification of necessity, and a slow erosion of the original founding principles as each new generation reinterprets the mission through its own lens. Now, imagine that same pattern playing out inside a sealed metal cylinder with a crew that cannot leave, cannot call for outside help, and is raising children who never chose to be born into the experiment in the first place. There's also a colder, more uncomfortable question buried inside the generation ship idea, one that almost nobody wants to actually sit with. The first generation who boards that ship consists of volunteers, adults who made an informed, willing choice to spend their lives in a metal tube for the sake of a distant goal. But every generation after that, they didn't volunteer for anything. They were born into a sealed metal box, inherited a mission they never agreed to, and will live and die without ever seeing a blue sky, without ever feeling wind, without ever having the choice to opt out of the project their ancestors started. That's not colonization. That's several generations of human beings born into permanent, inescapable confinement for a goal decided by people who died centuries before they were born. It raises questions that are less about rocket science and more about whether we would even have the right to do that to people who don't exist yet. Cryogenic freezing sounds cleaner on the surface. Just put the crew to sleep and wake them up when they arrive. Except we have never, in the entire history of medicine, successfully frozen and revived a complex mammal, let alone a human being, without catastrophic cellular damage. Water expands when it freezes, and human cells are mostly water, which means freezing a human body causes ice crystals to form inside individual cells, physically rupturing them from the inside. This isn't a technology we're refining, it's a technology we don't have the faintest working prototype of. Cryonics companies that freeze bodies today are, medically speaking, performing a preservation ritual with no scientific evidence it can ever be reversed, not a proven medical procedure. Betting an entire interstellar mission on solving a problem we haven't even begun to solve in a laboratory setting is optimism dressed up as a plan. And sending only embryos, frozen and later grown by artificial wombs, and raised by robotic caretakers on arrival, avoids the aging problem entirely, but creates arguably the most ethically troubling scenario of all three. You would be deciding right now to create human beings who will open their eyes for the first time light years from Earth, raised by machines, with no biological parent, no human community, no cultural continuity, expected to somehow build a functioning society from scratch based on programming decided by people who will have been dead for centuries by the time those children take their first breath. Every single proposed workaround to the interstellar lifespan problem carries a cost that isn't measured in fuel or dollars, it's measured in human dignity, and that's a cost that never shows up in the physics equations, but it absolutely should show up in the conversation. There's one more obstacle we haven't talked about yet, and it has nothing to do with physics at all, which is exactly why it gets ignored so often in these conversations. Even if every single technical problem we've covered tonight got solved tomorrow, there's still the question of who pays for it and for how long. The Apollo program, which only had to solve the comparatively tiny problem of reaching the moon, a destination roughly 400,000 kilometers away, not 40 trillion, consumed something like 4% of the entire United States federal budget at its peak, a level of sustained public spending on space exploration that has never been matched since, and realistically may never be matched again outside of wartime level national mobilization. The International Space Station, humanity's most expensive single object ever constructed, cost well over $100 billion and required continuous funding and cooperation between multiple nations for decades, just to keep a handful of astronauts alive in orbit a few hundred kilometers above our heads. Now, scale that up. An interstellar mission wouldn't take a decade of funding. It would take centuries, possibly longer than any single government, company, or civilization in recorded human history has ever maintained a consistent, unbroken policy on anything. Governments change, priorities shift with every election cycle, every war, every economic downturn. Companies go bankrupt or get bought out. Even entire nations rise and fall within centuries. What kind of institution, funded by whom, answerable to whom, could realistically guarantee uninterrupted support for a project that won't show any results, won't return any profit, and won't even reach its halfway point within the lifetime of anyone who approved the funding in the first place? This is why some economists and historians who study the sociology of large-scale projects argue that interstellar travel isn't just a physics problem or an engineering problem. It's fundamentally a governance problem, and it might be the least solvable one of all, because it requires a level of species-wide, multi-century patience and cooperation that humanity has never once demonstrated on anything in our entire recorded history. Now, I know what some of you are already typing in the comments, and I want to address it directly instead of waiting until the end, because it's the single most common objection to everything I've said so far. What about time dilation? What about relativity? Doesn't Einstein give us a loophole here? And the honest answer is, sort of, but not in the way people think. Time dilation is real. It's been experimentally confirmed thousands of times, most famously by putting extremely precise atomic clocks on airplanes and comparing them to identical clocks left on the ground. The faster you travel relative to something else, the slower time passes for you relative to that thing. If you could somehow accelerate a spacecraft to 99.99% of the speed of light, which remains physically impossible for reasons we already covered involving fuel and energy, the crew on board might experience a trip to a distant star that takes only a handful of years from their own perspective, while decades or centuries pass back on Earth. In theory, if you got close enough to light speed, you could cross the entire observable galaxy within a single human lifetime, from the traveler's point of view. It sounds like the perfect solution. But look closer, and you'll see it doesn't actually solve the problem, it just changes which side the problem lands on. Because while the crew experiences a short journey, Earth does not. Earth experiences the full, brutal, unshortened wait, decades, centuries, sometimes millennia, depending on the destination. Which means anyone who leaves on that ship says goodbye to everyone they've ever known, forever, and arrives at a destination where, even if they turn around and come straight back, the civilization they return to will be unrecognizable, separated from the one they left by a gap of time so large that language, culture, government, and technology will have moved on entirely without them. Time dilation doesn't make interstellar travel easy. It just makes it a one-way trip through time as much as space, A kind of exile so complete that the person who left and the civilization that sent them will never truly reconnect, even if the spacecraft itself survives the journey. Let's zoom out for a second, because I think it's worth actually confronting why this matters, why any of this should bother you beyond just being an interesting physics puzzle. For most of human history, the story we've told ourselves is one of expansion. We left Africa and spread across every continent. We crossed oceans in wooden boats that, by modern engineering standards, should never have survived open water. We climbed the tallest mountains, dove into the deepest trenches, and eventually broke the bonds of gravity itself and walked on another world. That expansion narrative is baked incredibly deep into how we understand ourselves as a species. This idea that no frontier is permanently closed, that given enough time, we always find a way. And that narrative has been right, over and over, for the entirety of recorded history, which is exactly why this conclusion feels so uncomfortable. Because the wall we're hitting with interstellar travel isn't a wall of ignorance, the kind we've broken through before with cleverness and persistence. It's not like the ancient assumption that heavier than air flight was impossible, an assumption based on incomplete understanding of aerodynamics that a few decades of engineering completely shattered. This wall is built out of the actual, confirmed, repeatedly tested laws of physics themselves, the speed of light as an ultimate speed limit, the brutal exponential math of the rocket equation, the finite and currently unbeatable production limits of antimatter, the unavoidable presence of interstellar dust at relativistic speeds. These aren't gaps in our knowledge waiting to be filled in by a clever engineer in a garage somewhere. These are the actual measured rules the universe runs on. I want to be fair here, though, and give proper weight to the strongest counter-argument, because I don't think it's honest to pretend there isn't one. Throughout history, people have confidently declared certain things scientifically impossible right before they happened. In 1903, the same year the Wright brothers achieved powered flight, a prominent scientist published an article confidently declaring that heavier than air flying machines were, quote, unavoidably, mathematically impossible. Close paraphrase there, because I'm not going to read you the exact line, but the sentiment was that clear and that confident. Lord Kelvin, one of the most respected physicists of his era, reportedly dismissed the idea of radio and heavier than air flight as fantasy just years before both became reality. So there's a real documented pattern of serious, credentialed experts confidently declaring things impossible right before those exact things happened. Doesn't that suggest we should be humble here too? Doesn't that suggest interstellar travel might be our generation's version of the same mistake? It's a fair question, and I don't want to dismiss it, but here's the key difference, and it's a difference that actually matters. The people who dismissed powered flight weren't wrong about physics, they were wrong about engineering. The physics of lift and thrust already worked. Birds had been demonstrating it for millions of years. The only missing piece was building an engine light, enough and powerful enough to generate sufficient thrust, which is a solvable engineering problem, and it got solved within a decade. But the speed of light isn't an engineering limitation waiting for a clever workaround. It's baked into the fundamental geometry of the universe itself, confirmed by more than a century of experiments. From particle accelerators to GPS satellites that literally have to correct for relativistic effects every single day just to function correctly. Nobody has ever, in any laboratory, under any condition, observed anything with mass moving faster than light, or even reaching that speed. This isn't a gap waiting to be filled by a smarter engineer. It's a wall we've tested from 1,000 different directions, and it has held every single time. That doesn't mean absolutely nothing new will ever be discovered about physics. Of course, our understanding will keep evolving, but it does mean that betting an entire species' future on overturning one of the most rigorously tested laws in all of science is a very different kind of bet than betting on better engines. Let's talk about something that connects all of this to a mystery a lot of you have probably wondered about at some point, usually late at night, staring up at a genuinely dark sky. If the universe is so vast, containing hundreds of billions of galaxies, each with hundreds of billions of stars, many of which we now know host planets, some of which sit comfortably in habitable zones, then statistically, shouldn't there be other intelligent civilizations out there? And if there are, where is everybody? This is called the Fermi paradox, named after physicist Enrico Fermi, who reportedly posed this exact question over lunch with colleagues in 1950. Given the sheer number of stars and the amount of time the universe has existed, even a civilization expanding extremely slowly, using nothing more advanced than what we've discussed today, should theoretically have had enough time to spread across an entire galaxy multiple times over, given the billions of years galaxies have existed. So why haven't we seen any evidence of that? Why is the sky silent? Now, to be fair to the topic, this isn't the only serious explanation scientists have proposed for the Fermi paradox, and I don't want to pretend it's the consensus answer, because there isn't one yet. Some researchers favor what's called the Great Filter hypothesis, the idea that there's some incredibly difficult evolutionary or technological step that almost no civilization successfully passes through, whether that's the origin of complex life itself, the jump from simple to intelligent life, or a civilization surviving its own technological adolescence, nuclear weapons, engineered pathogens, runaway artificial intelligence, without wiping itself out first. Under that theory, the universe might be full of dead civilizations, or full of planets that never got past bacteria, rather than full of civilizations quietly trapped in their own solar systems. Others propose the zoo hypothesis, the more unsettling idea that advanced civilizations exist and are aware of us but deliberately avoid contact, treating young civilizations like Earth the way a conservationist treats an untouched ecosystem, observing from a careful distance without interfering. And there's the dark forest hypothesis, popularized more recently in science fiction but taken seriously by some researchers, which suggests that advanced civilizations stay silent and hidden on purpose, because broadcasting your location to the universe might be less like sending a friendly hello and more like lighting a signal fire in a forest where you don't know what else is hunting. I'm not telling you any of these is correct, nobody currently can, but I wanted to give you the full picture rather than pretend the physical barrier explanation we've spent this video building toward is the only serious idea on the table. What I will say is that it's the explanation that requires the fewest extra assumptions. No hostile aliens, no hidden conspiracies, no unexplained mass extinctions, just the same laws of physics we've already proven true from every angle we know how to test, applied consistently to every civilization everywhere. In science, when you have multiple explanations and one of them doesn't require you to invent anything new, that's usually the one worth taking most seriously, even if it's also the least dramatic. Everything we've talked about today offers one of the most scientifically grounded, least exotic answers to that question. Maybe the silence isn't because we're alone, and it isn't because advanced civilizations are hiding from us, or destroying themselves before they get the chance to expand, though those remain possible explanations too. Maybe the silence is simpler and colder than that. Maybe every civilization that has ever existed, everywhere in the universe, has run into the exact same wall we're running into right now. The same crushing math of the rocket equation. The same lethal radiation environment of deep space. The same impossibility of exceeding light speed. The same fragility of biological life outside the narrow, protective bubble of its home planet. If that's true, and I want to stress this is a real hypothesis discussed seriously in academic literature, not a fringe theory, then it means intelligent life across the entire universe might be permanently, physically isolated. Each civilization trapped inside its own solar system like a message in a bottle that can never actually be delivered, staring out at billions of other bottles it will never reach and will never be reached by. That's either the loneliest idea you've ever heard, or, depending on how you look at it, one of the most quietly reassuring, because it means we are not being ignored by more advanced civilizations. there may not be anyone out there capable of finding us at all. And if any hostile ones exist, they're stuck exactly where we are too. Now, I promise you this video wasn't going to just be 50 minutes of bad news, so let's talk about what's actually still on the table. Because there's a really important distinction that gets completely lost in most conversations about this topic. And understanding it changes the entire emotional tone of everything we've discussed. There is a massive, meaningful difference between leaving the solar system, which we've just spent the better part of an hour establishing, is somewhere between astronomically difficult and physically impossible for biological humans, and expanding throughout the solar system, which is a completely different challenge, orders of magnitude more achievable, and one we are already taking real, concrete steps toward right now, today, with technology that either already exists or is realistically within reach in the coming decades. Mars is roughly 225 million kilometers away on average, not 40 trillion. A trip there takes around 7 to 9 months with current chemical propulsion, not tens of thousands of years. Radiation exposure on a Mars mission, while serious and absolutely a real engineering challenge that needs solving, is a problem measured in months, not decades, which makes it survivable with proper shielding and mission planning, not an inevitable death sentence. The asteroid belt contains an almost unimaginable amount of raw material, metals, water ice, and other resources that could theoretically support space-based industry without ever needing to be hauled up out of Earth's deep gravitational well in the first place. Serious engineers and physicists, going back to Princeton physicist Gerard O'Neill in the 1970s, have designed detailed, physically plausible concepts for enormous rotating space habitats, sometimes called O'Neill cylinders, that could use simple rotation to simulate gravity, house tens of thousands of people, and be constructed largely from asteroid or lunar material rather than material launched from Earth. These aren't science fiction fantasies floating on pure imagination. They're grounded in real orbital mechanics and material science, the kind of engineering that doesn't require us to break a single law of physics. Just an enormous amount of persistent, patient effort across many decades. None of this means Mars is easy, and I don't want to leave you with the impression that expanding through our own solar system is some simple next step compared to the interstellar problems we spent the last half hour on. Mars has essentially no meaningful magnetic field, which means its surface receives dramatically more radiation than Earth's, roughly comparable to what an astronaut would absorb spending extended time outside the protection of the International Space Station. Its atmosphere is thin enough that surface pressure sits at less than 1% of Earth's, meaning any breach in a habitat wouldn't just be uncomfortable, it would be instantly, catastrophically fatal with no margin for error. Dust storms on Mars can occasionally grow large enough to encircle the entire planet for weeks at a time, choking out sunlight and threatening any technology relying on solar power. The soil itself, called regolith, contains perchlorate compounds that are toxic to humans and would need extensive processing before any crop could safely be grown in it. None of these are unsolvable. They're genuine engineering and logistics problems that serious mission planners are actively working through right now, but they're also not small. And anyone who tells you Mars colonization is a simple, near-term weekend project hasn't looked closely at the actual environment we're talking about. The honest version of this story isn't that expanding through the solar system will be easy. It's that it's achievable, difficult, but achievable with physics we already understand and engineering we can realistically improve on, which puts it in a completely different category from everything discussed earlier in this video. This is genuinely a believable future. Mining outposts on the moon, research stations, and eventually permanent settlements on Mars. Massive rotating habitats scattered through the asteroid belt, self-sufficient, powered by solar energy so abundant it's essentially limitless once you're past Earth's atmosphere. Humanity spreading throughout our own solar system over the coming centuries, becoming a genuinely multi-planet, multi-habitat species, without ever needing to solve the impossible math of interstellar travel at all. And here's the part that I think gets lost in most of these conversations. The part that actually reframes everything we've talked about tonight. If humanity does eventually build that kind of civilization, spread across Mars, the moon, the asteroid belt, dozens of rotating space habitats housing millions of people who have never set foot on Earth and never will, then the entire premise of needing to leave the solar system becomes a lot less urgent. Because we would have already solved the problems that make interstellar travel seem so desperately necessary in disaster scenarios. Overpopulation on Earth, a planet-destroying asteroid impact, resource scarcity. All of those existential threats become dramatically less terrifying if humanity is no longer confined to a single planet, even if we remain confined to a single solar system. The dream of becoming a multiplanetary species and the dream of becoming an interstellar species get conflated constantly in popular culture, in movies, in comment sections, but they are not the same goal, and only one of them is realistically achievable with technology. We can actually see a path toward from where we're standing right now. There's an interesting historical comparison worth making here too, one that I think actually cuts against the easy optimism people usually reach for, rather than supporting it. People love comparing interstellar travel to the age of ocean exploration, pointing out that European sailors once feared crossing open water in wooden ships. And yet, within a few centuries, humans were circling the entire globe. It's a comforting comparison, but it quietly ignores a crucial difference in scale. The Atlantic Ocean is a few thousand kilometers wide. A sailing ship in the 15th century could cross it in weeks to a couple of months, using wind, a renewable, freely available energy source that required no fuel to carry along. The sailors on those ships could breathe the air around them, could in theory catch fish and collect rainwater if supplies ran short. And even in the worst case, a failed voyage meant death for that specific crew, not the collapse of an entire self-contained civilization sealed inside a metal hull. Every single one of those forgiving conditions disappears the moment you leave Earth's atmosphere. There's no wind in the vacuum of space to push a sail, aside from the faint pressure of sunlight itself, which is why light sail concepts like Breakthrough Starshot work for tiny probes, but not for anything carrying people and life support. There's no air to breathe if something breaks. There's no rainwater to collect, no fish to catch, no coastline to spot on the horizon if you got the navigation wrong. The comparison to ocean exploration isn't wrong, because humans lack the same spirit of exploration we had 500 years ago. It's wrong because it compares a genuinely hard but survivable problem to one that breaks some of the most fundamental laws of physics we've ever confirmed. That doesn't make the comparison meaningless as inspiration, but it does make it misleading as an actual argument for feasibility. And I think it's important to be honest about that distinction instead of reaching for a comforting historical parallel just because it feels good to say out loud. I think there's also something worth sitting with here that has nothing to do with rocket science at all. There's a strange kind of comfort hidden inside everything we've talked about tonight, if you're willing to look at it the right way. We live on a planet that, out of the entire observable universe, out of every star and every world we have ever detected, remains the only place we know for certain that life exists. Not the only place life could exist. We genuinely don't know that, but the only place we have actual, confirmed, undeniable evidence of it. Every single person who has ever lived, every civilization that ever rose and fell, every war, every love story, every scientific discovery, every piece of art, every sunset anyone has ever watched happened on this one. Small, blue planet orbiting an unremarkable star in an unremarkable corner of an unremarkable galaxy. And instead of that being a small, sad fact, I think there's an argument that it makes this planet almost unbearably precious. Not a launching pad we're desperately trying to escape from before the clock runs out. Not a doomed rock we need an exit plan for. The only known home for consciousness in an unimaginably vast, mostly silent universe. Carl Sagan, writing about the famous photograph of Earth taken from billions of kilometers away by the Voyager spacecraft, a photograph where our entire planet appears as a single pale dot of light suspended in a sunbeam, wrote about how that image should reshape how we treat each other, how we treat this world, precisely because it might be all we ever get. And after everything we've walked through together tonight, all the math, all the physics, all the brutal engineering realities, I think that idea lands differently than it would have 50 minutes ago. So where does that leave us? I don't think the honest answer is despair, and I don't think it's blind, unscientific optimism either. I think the honest answer sits somewhere in between, and it's actually a more interesting place to land than either extreme. We are, almost certainly, a species that will live and die within this one solar system, at least for as long as any of us can meaningfully predict, and quite possibly forever. That is a genuinely strange thing to fully accept, because it goes against nearly every story we've ever told ourselves about our own destiny. Every science fiction future we grew up dreaming about, every childhood fantasy of alien worlds and starships. But being confined to one solar system is not the same as being confined to one planet. And there is an almost unimaginable amount of exploring, building, and discovering left to do right here, on the moon, on Mars, throughout the asteroid belt, and eventually maybe in habitats we haven't even designed yet, floating between worlds that have never known a human footprint. That future doesn't require us to break the laws of physics. It just requires us to actually try, consistently, patiently, across generations, the same way every meaningful thing humans have ever built required exactly that. Before you go, I genuinely want to know where you land on this, because I've read through thousands of comments on videos like this one, and the disagreement is real, it's not manufactured drama. People actually see this completely differently, and I think that's what makes it worth talking about. If you think interstellar travel is permanently off the table for biological humans, and everything we just walked through convinced you of that, say so in the comments, and tell me which specific piece of this convinced you the most. Was it the rocket equation, the radiation problem, the interstellar dust, or something else entirely? And if you think humanity will eventually find a way around all of this, whether through physics we haven't discovered yet, some approach to propulsion nobody has proposed, or a version of humanity that isn't fully biological anymore, I want to hear that argument too, laid out properly, not just we'll figure it out, but the actual reasoning behind why you believe that. Tell me what you think the missing piece is. If you're someone who works in physics, aerospace engineering, or a related field and you think I got something wrong or oversimplified, say exactly what. Because I would rather have that conversation in public than pretend this topic doesn't have real, ongoing scientific debate attached to it. And if this video actually changed how you think about our place in the universe, even a little, even just for tonight, let me know that too. Because that reaction, more than anything else, is the entire reason I make these. One last thing before we close this out. Somewhere out there, on some clear night, decades or centuries from now, someone is going to look up at the same stars you're looking at right now, and they might be standing on the surface of Mars instead of Earth. They might be inside a rotating habitat built from asteroid metal, watching sunlight pour through reinforced windows their great-grandparents helped design. They won't have reached another star system, they probably never will, but they will be living proof that a species born on one small planet managed to spread itself across an entire solar system anyway, slowly, patiently, without ever needing to break a single law of physics to do it. That future is still completely within reach. It doesn't require warp drives or wormholes or antimatter engines we can't build. It just requires us to keep going. And honestly, maybe that's a better, more human story than the one where we just skip straight to the stars anyway. If you made it this far, drop a comment and tell me one thing you learned tonight that you didn't know before you clicked on this video. Because I genuinely read every single one, and I want to know which part of this actually stuck with you. Thanks for spending this time with me tonight, and I'll see you in the next one.